Chapter 7, this module is on work and energy. So first of all, it's important to understand that you can only do work if the object moves. So here's the equation to calculate work. Work is equal to F, the magnitude of the force vector, times D, the magnitude of the displacement vector, times the cosine of the angle between the force and the displacement vector. So F and D are scalars, so they are not negative. Do not put a positive or a negative sign on force or displacement because they're just magnitudes. The angle, the cosine of the angle will take care of the sign of the work. So work is a scalar quantity. It can be either positive or negative. The positive or the negative sign comes from the cosine of the angle. Okay, now let's look at an example. So let's assume you have a block of mass M and you apply a force F1 to the right and also force F2 as shown in the diagram. And if I ask you to draw a free body diagram for this block, it's easy because we have already learned it. We have to first specify positive x direction and positive y direction. And next step is to identify all the forces acting on the object. Weight is acting directly downwards. It's always directly downwards in negative y direction based on my coordinates. And then you have a force F1 applied to the right. And force F2 is applied at an angle of theta degrees above the horizontal. And normal force is acting directly upwards. And the next force is the kinetic friction force. Let's assume the object is moving to the right, so there's a relative motion between the object and the surface it is in contact with, so it is kinetic friction. So now let's see the steps to draw a work diagram. So you have to first draw an arrow to represent the displacement vector, making sure to draw the arrow in the actual direction the object moves, and then draw an arrow to represent the force, making sure to draw the arrow in the actual direction the force is in, and label the angle between the two vectors you drew, whether it's 0, 90 or 180, and then just repeat for each force for which you are calculating the work. So I'm going to draw work diagrams for our example. So let's start by drawing the displacement vector. The object is moving to the right, so displacement vector is to the right. And then force F1 is applied at an angle theta degrees above the horizontal. So the work is equal to F2 times the displacement D times cosine theta. And F2 and D are just magnitudes. And then let's look at the next force, F1. F1 and D are both acting in the same direction, so the angle between the force and the displacement is just 0. Cosine 0 is equal to 1, so work would be just F1 times D. And then next, let's look at the kinetic friction force. Kinetic friction opposes the motion, so displacement vector is to the right and then kinetic friction force is to the left. An angle between the two is just 180 degrees. Work is equal to magnitude of the kinetic friction times the magnitude of D times cosine of 180, which is equal to negative 1. So you get negative FKD. The negative sign comes from the cosine of the angle. I didn't put a negative sign for the kinetic friction. Okay, now let's look at the weight. Weight is acting directly downwards, displacement is to the right, and the angle between the two is 90 degrees. Cosine of 90 degrees is equal to 0. So you need to understand whenever the force and the displacement are at an angle of 90 degrees apart, work done on the object by that force would be 0. So normal force is upwards, displacement is to the right, angle is 90 degrees, so work done by the normal force would be just 0. So these are the work diagrams for all the forces acting on the object. And now let's see the non-conservative forces and conservative forces. So if you look at the forces acting on an object, we can talk about two types of forces, conservative and non-conservative. The difference is the work done by a non-conservative force is path dependent, and then work done by a conservative force is path independent. And let me write it down first. So work done by a non-conservative force is path dependent. It depends on the path. And work done by a conservative force is path independent. So in this course, this is Physics 111. So in this course, we learn about two types of conservative forces. That would be force of gravity and spring force. All the other forces except for force of gravity and spring force are considered as non-conservative forces. So you might be wondering why I'm talking about conservative forces and non-conservative forces. There's a reason for that. We are going to use the work done by these non-conservative forces in our energy equation. So I'm going to explain the energy equation after we discuss about these conservative forces and non-conservative forces. So examples, force of gravity and spring force for the conservative forces, and non-conservative forces. Everything else we learn in this course are non-conservative forces. Okay, so now let's move on to the seventh term, conservation of energy equation. So all the energy in the universe is constant. So we say that energy is neither created nor destroyed. So you can see I subscript I represent that this is the initial energy of the system, and F represent that is the final energy of the system, and W and C is the work non-conservative. So if you talk about energy in a system, so energy can go into the system or energy can go outside of the system. So in order to account for that, we use the work non-conservative in this seventh term, conservation of energy equation. So whatever the energy you had initially, EI plus work non-conservative would be equal to final energy of the system. This work non-conservative can be either positive or negative. If it is positive, energy goes into the system. If it is negative, energy goes outside of the system. And let's understand this PEG. So what is PEG? PEG is the gravitational potential energy, and you're going to learn an equation to calculate the gravitational potential energy. That would be just mass times G 9.8 times the height. And then spring potential energy. Spring potential energy depends on K, the stiffness of the spring, and X, the compression or the extension in the spring. And then kinetic energy, it depends on the mass of the object and also how fast it is moving, speed. So this V in the kinetic energy equation is just the speed, not velocity. Energy is a scalar quantity. So that would be it.